I'm Luis Ceze. I'm co-founder and CEO at OctoML, and I drink French press coffee black. I'm not espresso drinker, so.
Dude, I just gotta say it. We're matching today, and we did not plan this at all.
Until you said that, I didn't notice, but you're absolutely right. Oh my God, that's literally the same shade of green. That's embarrassing.
Exactly. And it's not the most common shade of green. And so for those that are just listening, Mihail and I are both wearing t-shirts, and it's both like this mint green color. And we just talked with Luis Ceze, who, wow, he was special, man. This was really cool. And I love how everything, like he just must see the world and bring everything back to like computing. It feels like everything he sees, he's like, oh yeah, that's like the same as when we're doing that with computers.
Yeah. I love it. I thought it was fantastic. I was totally nerding out during this entire conversation, just like as he was going down these rabbit holes of like talking about hardware targets and how that relates to their efforts at OctoML, tying that into the broader vision of what we should do. What's the next frontier? Basically, bio-based computation and how we can leverage different that for solving computational problems. And then of course how it tied into at the very end, just talking about books that he reads and how that also is a metaphor for computing.
One thing that I absolutely loved from him and his vision, I feel like he's got a really strong vision. He's got a really great way to articulate things. I was geeking out listening to you all geeking out, and how he mentioned he sees a future where you don't need to think about infrastructure. You should just be able to do what you got to do, and infrastructure happens. And this is interesting because Ketan, who is also in Washington and he's leading Union.ai, he told me that same vision. And it feels like there's something there. If he's seeing it, Luis is seeing it, people are understanding that there is a lot of complexity underneath the hood, and that most data scientists or machine learning engineers, when they start deploying things, or even when they're before the deployment process, they shouldn't have to be worrying about what's the most efficient way for me to do this.
That's absolutely right. And that is a trend, I think, in a lot of technological paradigm shifts, where it starts with everyone needs to know everything, and then as the number of options and things that you have to keep track of, right, in terms of how many different hardware systems you need to accommodate, how many different software systems you need to accommodate, how many different modeling frameworks you need to accommodate, there comes this question of, that's like the unbundling of the ecosystem, right, where everything is just going all over the place. And then there's this rebundling that happens when someone decides, wait a second, like I don't feel that random person starting as an MLE tomorrow should have to worry about, am I compiling an x86 computational architecture, or is this, is it something else? Or am I using an NVIDIA GPU, or am I going to, Intel CPU versus X, Y, or Z thing? So that makes a ton of sense to me. That's just something that we shouldn't have to deal with, and most practitioners should focus on the things that they really need to be focusing on, which, for a lot of purposes, is just the modeling, the data concerns, right? And I'm all in favor. I'm all in favor of this movement.
So what else is interesting about that is we had on the podcast, I think like 2 months ago, this guy named David, and he works at LexisNexis, and he had around 12 PhDs really working on low-level things in the company to help with speed and compiling, and especially when it comes to data. And he was talking about how he does not want a machine learning engineer doing those kind of tasks. And he also really wants it to be the most efficient. And so what it feels like Luis is doing, and Ketan, and I'm sure there's probably others out there that I don't know about, is they're trying to bring that benefit to the world without you needing the 12 PhDs to be working on it. So exactly right. I love that he's doing it. I love that we got to speak a little Portuguese with him. Well, I got to speak a little Portuguese.
I got to hear Portuguese. I was listening to Portuguese. I was.
There you go.
I enjoyed that. And very nice language.
Very nice. So last thing that I will mention is we're doing all kinds of local meetups. So if you are interested in doing a local meetup, get a hold of us. Mihail is organizing the local meetups in San Francisco. We got all over the US, they're happening. All over Europe, they're happening. In India, they're happening. And super cool, which I think we should just have a little excursion to the first one in Australia. It's happening there in Sydney. So,
Wow.
dude, yeah. Actually, in Africa too. I think they're going to start doing it in Nigeria and potentially South Africa. So,
Wow.
yeah, we're
Global.
having it happen, man. This
You're
is
Mr.
super
Worldwide, man.
cool. Yep. That's it. That's what we're trying to do here.
You and
So-
Pitbull, Mr. Worldwide.
That's the only sentence, the only way that I can be compared to that guy. I think I am not as cool as him in any other way, but
In your community, you are as cool. In your small niche.
there it
community.
is. There it is. So yeah, so get at us. And without further ado, let's jump into the conversation that we just had with Luis. If you want to find out more about the local meetups, you can find us on meetup.com or just jump in the Slack, and there's probably a city channel named after the city that you're in. All right, that's all. So we were just talking about how we got to keep this fun and fresh and make it interesting because there is boring content out there. So I got to ask you, Luis, I did a little research before we hopped on this, and you were on a podcast not too long ago, and you professed that MLOps does not exist. So I gotta say, like, I took that personally. You're coming out of my
No.
lifeblood, man. What's going
What?
on here? Explain yourself.
lose-
You-
Did we
I
Oh,
think
no.
we're losing Demetrius in a
Was
very
it-
dramatic moment in the podcast. Well, you see, when you said
Wait.
that, it's just so true that the internet, confirmed it. No,
broke?
Am I back? Wait, am I back?
Yeah,
Am
you're
I
back. You're back.
Your voice is
This-
back.
It was so
Wait, your
good.
voice
My
is
voice
back,
is
but-
back, but I'm frozen. Hold on.
Is that just for me, Luis, or is it also for you?
No, he was frozen for me as well.
Okay,
You can leave it in the
And-
podcast. This will be fun,
MLOps is dead.
And then all of a
Exactly.
sudden,
Crashed the
No. All right. So Cece said that, like, hi everyone, thanks for having me in the podcast. I can tell this is gonna be fun and interesting. So I want to qualify that. What I mean now, let me put my academic hat, like we we're talking about. Just been thinking about this for a while, right? So just a bit of my history that's relevant to our discussion here. I've been doing work in the context of high performance computing in various forms. I started in the Blue Gene project doing linear algebra and hardware accelerators and hardware design for life sciences. And then for most of my academic career, I've done work on hardware software code design for emerging applications, and I've been using machine learning as a workload to motivate this research for a while, right? So now that means that, of course, as an academic, I'm going to have strong opinions, but now as a startup CEO building a product, I'm also going to have strong opinions about what I think, this is the market opportunity and how we actually get machine learning, which has proven to show that it can solve a lot of awesome problems. It's actually permeating in all of the interesting applications we can think of involving computers today have a machine learning component, right? So that means it's really reaching the level of maturity that we have to be very principled about how we deal with it, how we deploy it, how do we make machine learning models an integral part of applications, right? So of intelligent applications. And now to qualify what Dimitri started with, the MLOps is dead. So what I want to say is that here's how I think about it, right? So machine learning models, they have code and they have data, right? So and together, they perform computations that honestly we didn't even know how to express with just code in the past. The magic of this is using a ton of data to guide how a blob of code behaves to do amazing things like computer vision, natural language processing, and so on. Now, when I say the MLOps it should not exist, what I really mean is that a lot of what people call MLOps today, and we should talk a little bit about it because there's so many definitions of MLOps that can make it confusing, exists just because we cannot treat machine learning models as if you were any other piece of code once the model is ready to be deployed. I fundamentally believe that for machine learning deployment to reach a level of maturity that I think it needs to get for it to continue permeating all applications, we need to be able to treat machine learning models as if you were any other piece of code, okay? Once you're at that point, why not call it DevOps? Like if you do it right and you make a machine learning model, once it's ready for deployment, like an integral part of applications and use DevOps, I think we're in a good place. So that's what I really mean. All that said, the process of getting from a problem that you want to solve, collecting the data and producing a machine learning model that is actually ready to be deployed, that needs a flow that's special. We can call that MLOps. So that would be okay with me. I just don't want to confuse the model creation part with once you deploy the model, it's part of an application with MLOps. Does that make sense now, or did I?
Yeah,
Are
yeah,
you
I love
breathing
it.
easier now, Demetrius? Are you breathing easier now?
I mean, he's unfrozen, right? So now he's okay.
That's right. Yeah, he unfroze.
I unfroze. Oh man, that is hilarious.
Yeah. So,
Well, I
um,
sorry, like just maybe one. So it sounds like what you're saying here is that it's more about like the semantics. It's kind of like a semantics argument. Like there's still the DevOps, which is a DevOps piece, but but fundamentally there's this additional component. Maybe we're conflating the term MLOps to encompass more than it really should be subsuming. Namely, some of this more like operationalization of just resources and things like that, which is more of a traditional software engineering problem.
yeah, and also operationalization, but also integration with the application, right? So remember that we have to be careful not to think that the machine learning model is the entire application, right? So of course, machine learning engineers, they are at a premium, they're doing awesome things, but we cannot forget that what makes a machine learning model amazing is when it's embedded in an application that people use and pay money for and create, businesses around it and so on. Machine learning model does not exist in isolation. There's a bunch of stuff around it that makes it useful and reaches people's hands, right? So, and I think that's the part that is a huge opportunity today, because the way I think about it, and part of this is obvious, is that there's all this wonderful machine learning innovation that happen. Like it's just incredible to see every day we see a new machine learning model that does amazing things, right? So, but then you have these applications on the other hand that people actually use. There's a huge gap between those, and then this gap involves a lot of manual engineering, involves a lot of work to actually put a model into production, right? So, and we should improve both sides. Of course, we should continue making the process of creating machine learning models easier, so we continue to accelerate innovation there, and create sort of like this pool of awesome things that you can put into applications. But also you need to work on putting a very systematic process to turning that into applications, so it actually reaches a broad audience, right? So, and if you don't mind, like, I'd love to go a bit deeper on the deployment side, So in terms of my background, like, I can talk for longer than you probably want me to about model
No,
deployment.
keep it
We
going,
can
man. This
we
is
can
great.
talk a lot about the core machine learning side as well, because we do have some passions there we can discuss. But let's talk a little bit about the deployment side. So, you know, um, it's interesting to go through the exercise of thinking about why are we not treating machine learning models as if you were any other piece of code today. First is it's highly dependent on the hardware, right? So, naturally, machine learning models fundamentally become high performance linear algebra code that needs to run well, and that involves using the hardware to the maximum extent possible, right? So that's the way it's being done so far basically boils down to very talented programmers writing low level code to make very tight loops using specific data types and using specific instructions in processors or in GPUs or in accelerators to keep utilization at the peak as high as possible. That involves a lot of artisan code, right? So, and that typically needs to evolve with the model, right? So as new models do new things, there's new operators that have to go and generate new, very hardware dependent code. So to pop up, what does this mean from, it's almost like from an industry perspective? We saw really tight coupling between the hardware and the software stack on top of it. So arguably, NVIDIA is where it is today in machine learning because they did a fantastic job with CUDA. CUDA made it a lot easier for folks to go and program a parallel machine that a GPU is. Parallel computers have been notoriously hard to program, right? So this is a decades-old problem in academia and a decades-old opportunity in the industry too, right? So starting from the supercomputing days all the way to machine learning today, right? So um, and this tight coupling is so strong that I like to make an analogy that looks like the mainframe industry in the 70s and 80s. Like if you bought IBM software, if you wanted IBM software, you had to buy IBM hardware, and if you wanted IBM hardware, you had to buy IBM software because it's the only thing that was available for that hardware, right? So, unfortunately, to a large extent, that exists in machine learning today, right? So every hardware vendor has its own set of system software for machine learning they have to maintain, And that created a lot of fragmentation in the industry, created a major complexity in deploying machine learning models, right? So once you put it in production, today, once you want to put a model into production today, you have to go and figure out what is the target that's going to run, which libraries you're going to use, or maybe if there's a compiler available, you're going to go and use that compiler and try it. Does it run faster? Does it work? You're going to validate it. And all of this creates this coupling that once you create a version for a machine learning model to be deployed on a specific hardware target, you're going to stick with it. Or you're going to do the work to support all of the other hardware targets that you need to support, right? So um, so this is so manual today that I think it stiffens how people deploy machine learning models. Either they go suboptimal, you just go in the cloud, pick an instance, and you scale whatever instance you got there, or you live with poor performance on the edge, or sometimes you don't even deploy a model to the edge because you don't reach the level of performance that you need to deploy that model, right? So anyways, I'd say that a lot of it boils down to hardware dependence. That we will talk about how we make much more portable and avoid the need for human tuning by taking fundamentally a compilation approach to machine learning as opposed to a translation library pinned approach, right? So anyways, I don't want to bore the audience going deeper and deeper on this, but I say like hardware dependency machine learning is something that I think is a serious problem that we need to solve. And once you decouple model from hardware, I think you're going to create opportunities on both sides, right? So
Yeah, I think there's something really powerful about what you're saying. And fundamentally, I mean, if I could paint like really broad strokes here, talking about just maybe different, like we're getting new abstraction layers around some of these concepts, right? This interface between the hardware and the software. And yeah, I mean, I remember back in college, taking parallel programming classes, going through the exercises of, SIMD kind of like programming models, doing stuff like actually having to code up CUDA kernels. And I think a lot of people that enter the field today don't recognize how far we've come even at this point compared to those earlier abstraction or those earlier kind of primitives that we had to deal with to do anything sensible from a programming standpoint, parallel programming standpoint.
yes, so well said, Mihail. Like yeah, thank you for acknowledging that. We made a ton of progress, but even to this day, like folks building machine learning models still think about, what hardware you're running. You think about performance early on when the model creation side. Imagine a world where this abstraction evolution goes even further, and when you create a machine learning model, all you think about is what is the best work that I can do with the data that I have to create the very best model, and not think about the hardware infrastructure, and let the system do that for you, right? So yeah, it's I think it's interesting that a lot of machine learning engineers, when you see resumes, they talk about the framework, they also talk about, oh, you can write CUDA code and write C++ code. Like I wish that all those brain cells went to all the cognitive cycles went to creating a better model, and not having to think about, you should even think about what the hard is running on. You should even think about CUDA or C++. It doesn't make any sense, right? So I think, and
Yeah.
not even less SIMD and threading, what kind of, but people have to do that today, right? So
Right. I mean, yeah, some smart people did a lot of the legwork to make it easier for the next generations, and maybe that's, I mean, this I think it ties really nicely into what your maybe OctoML and even the efforts of your project and the company, and is actually a pretty nice segue because in a sense, one of the things that OctoML seems like it was born out of TVM, right? And I actually remember using TVM in some of my own work back in the day.
oh,
A
great,
nice
thank you.
library, yeah. No, I mean, it's like it's a really nice library, and I'd love to just maybe dive a little bit into talking about the motivations behind that effort and how, and then eventually we can get into talking about how that evolved into
And we should
what
well, we
OctoML
should
has
probably
become.
start for
Yeah.
a few of us out there. Just like, can you explain what TVM is?
Yeah,
Yeah,
absolutely. Yes. So to that, yeah. So TVM stands for Tensor Virtual Machine, right? So there's a VM, a virtual machine analogy, because you have a clean interface over, that abstracts away hardware details, and you can map machine learning models into that interface, and then whatever comes underneath it should not be a concern for folks creating models, right? So, and I would say, so TVM started out of an effort, probably maybe 6 to 8 years ago, maybe more. And the question that we're asking then was the following: we have lots of machine learning models, we have lots of hardware targets. There is this, hardware dependent software stack. We think about how would we think about intermediate representation that you can translate models into, do a bunch of optimizations to make those models run well on whatever hardware target you have in a general way, such that you can extend to new hardware targets, and then progressively lower that to custom code for a given model on a given hardware. So This is why I wouldn't call it a library approach. It's really a compilation approach. Like we early on asked, and the first one to ask the question, like, can we turn machine learning model execution from an interpreted process, which is interpret the model and call library, to model in and fresh binary code out for that model on the hardware that you chose. So why I'm emphasizing this, I promise it's not to bore the audience, is that once you go from, library-based interpreted approach to a fresh code generation approach, you can do a lot of things that are very powerful, right? You can do high-level graph optimizations of your model, like you can fuse operators, say a matrix multiply with a convolution, you can do them together, so you get, locality benefits. You can do a lot of choice of like how should you order the computation in a way that is going to better match the hardware capabilities. And then as you go down, how do you automatically choose specific hardware instructions that are available on the processor or on the GPU that you're running that might not be available in others, right? So you keep hearing about Tensor Core today. These are, essentially dedicated hardware units that can do matrix multiply, for example. But to use that, you have to set up your code just right. But now, what if you were automatic? That's the question that we're asking. So that's what we did with TVM. So we took a compilation-based approach and coupled that with some special sauce that at that time was, okay, so when you're compiling a machine learning model to a given hardware target, there's literally billions of ways in which you can compile a given model on a given hardware target. The question is, how do you pick the very best option? Okay, so without trying them all, because to try and a billion combinations of code choices, compilation, and measurement, and trying, you're talking about centuries of compute or more. Like it's just impractical. That's when we use machine learning for machine learning code generation and to pick in a using predictive way how should you make these choices to compile your code. So I know this was a long, a long intro, but I wanted to emphasize what makes CVM special then, and I think was a huge driver of its traction because we not only made it very effective in generating code, but also make it easy to extend to other frameworks, easy to extend to other hardware targets. So we fast forward to 3, 4 years after creation, we started OctoML. TVM was about to become an Apache Software Foundation project. It had been using production for a while, at big hyperscalers, and hardware vendors started adopting it because it supported all the major frameworks and it made it easy to extend to new hardware targets. And fast forward to today now, TVM supports pretty much all of the major hardware targets that folks care about, and it supports all the major frameworks. And given the landscape of machine learning compilers and system software in general, TVM built bridges to all of the other pieces, and we're building more bridges to other compilers for machine learning as well, such that we offer a one-stop shop for folks to come in and get their models to run really well on hardware targets. So, was that an okay intro? Yeah, that makes sense. Yeah.
No, I think it's awesome. I mean, if I could even just like, just say it even in one just maybe pause here to say that I think that there's so many details behind what you just have said, but for people that are maybe newcomers to like data science or machine learning, I think that the key point is that when you do something as simple as like matmul or conv2d in your PyTorch code and your TensorFlow code, that there's a lot of optimizations that have to happen in the background to make this run efficiently, so you're not there waiting forever for something to actually run to completion. And that's really one of the core pieces, I think, of what you're discussing here is like all that extra level of optimization that needs to happen to make something efficient, to make it tractable, right, from a computation standpoint, which is like there really is a lot of detail here that people are able to disregard because of things like TVM, which is really astounding.
That's right. And then to your point, thank you. Yeah. So very well said. It's about, raising the level of abstraction such that you don't have to worry about performance early on, right? So you can go and use these matmul or convolutions and not worry about how is it going to run fast. And to be clear here, running fast is not a nice to have. In machine learning, making the most out of the hardware is an enabler. Otherwise, it's just, the amount of computation involved in doing one inference is just incredible compared to anything else that we use in computers, right? So yeah.
I'd love to go even a little bit, maybe to give more context here. Where does something like a TVM sit in the ecosystem of other efforts that have been made to provide these hardware-based compiler optimizations? When I think of something like a TensorRT or Onyx runtime, right, which are trying to maybe tackle similar problems or with maybe different approaches, where does it kind of sit in that whole ecosystem?
Yeah, great question. And TVM integrates with Onyx Runtime and TensorRT. The way to think about this is that So Onyx Runtime is made was made to be general, support a broad set of models and also some set of hardwares. It does take, primarily a library-based approach by having a very rich library of basic operators that are pre-optimized for harder targets that gives you some portability there. But the real question here is it can you do better by generating fresh code for your whole model or parts of your model on the hardware that you chose at a specific time? The way we integrate with Onyx Runtime is creating what we call an execution provider, where the model comes into Onyx Runtime, and when profitable, when makes sense, it generates fresh code. Okay, so and then TensorRT, by the way, is NVIDIA's answer to machine learning compilation to a large extent, and it's great, of course, because NVIDIA created the hardware; they understand the hardware properties, right? So, and they have a long history of writing high performance code for their own hardware, and that means they can do a fantastic job. But to a large extent, TensorRT is also specialized to the classes of models that NVIDIA cares about, of course, because of its customers, right? So where does CVM come in? And we do have collaboration with TensorRT folks in showing that it's a best of all worlds approach. Like, so the way we're not dogmatic, by the way. I want to make it very clear that we created TVM, we invest a lot of resources in TVM, but it's not that we see the world like should be only TVM. No, our goal here is to make models run really fast on the hardware produced because it saves the world, because it reduces the energy consumption of computers and makes people's life easier, right? So the reason I'm saying this is because we take a complementary approach. So if you take a model and you wanna and you have it happens to be NVIDIA hardware, what we do is we can show that, okay, parts of your model should go through TensorRT and parts of your model could go through TVM, and then you pick the best of each and you combine and produce a better model. Does that make sense? So, and I would say that in cases that TVM tends to offer an advantage are emerging models or things in the long tail that haven't received as much attention because those haven't been optimized by hand as much, right? So this is why I would say they're very complementary and offer parallel paths to deploying the model. So did I answer your question, Mihail? I know it might have been a long answer, but
No, no, absolutely. Yeah, I think that makes a lot of sense. So this, I think, also fits nicely into, so TVM was the genesis, and it sounds like TVM still forms the core of a lot of OctoML, but OctoML maybe is taking this one step further. Where are we going with that, or
yeah,
where are you guys going with that?
great. Thank you for asking. So, what we bring at OctoML is a machine learning deployment platform, right? So, what we want there at the highest level, back to the early conversation, we want to bring DevOps agility to machine learning deployments. What does that mean? It means offering hardware independence. So, you give your model to deploy, you never have to think about you don't even need to think about whether you're gonna use a library-based approach or compilation-based approach, or if it's NVIDIA, you're gonna use cuDNN or TensorRT TVM. Like, we abstract all of that away such that you have a flow that looks like model-in and deployable, portable, high-performance function code to run out that you can move around to different hardware targets. So if you're going to deploy it in the cloud, you could deploy in a given GPU. But then if you want to scale it up and the instance is not available, you can go and run on a different GPU and still make the most out of it, right? So what OctoML does is automates the whole process of exploring how your model runs on different hardware and produce runnable versions for every target that you choose. We support all major clouds: GCP, Azure, and AWS. We also support some edge targets, though our primary strike zone today, with customers is in cloud deployments. And then you can evaluate, how different versions of your model do in deployment by actually, giving you the ability to create multiple versions of your model and compare how they do with respect to each other. Price performance trade-offs, things like, say that what you want is a model to run inference B at 100 milliseconds or less. You don't care if you care if it's more than 100 milliseconds, but you don't care if it's 50 milliseconds. It just cares 100 or less. And then after that, what you care about, say, is throughput per dollar. For you to do that today, you'd have to go do manual work and a bunch of different things to figure out which one you should do it for. So OctoML automates all of that and produces the ability to choose that. So it abstracts away all the trade-offs that you think about, batching and concurrency and threading and so on. Like, it just tries a bunch of combinations there as well. And then he puts it in a package that can go and deploy it in the cloud or locally via Python will or .so library in a bunch of different packaging. So when I guess, stepping back and saying one line is model in and deployable code out, and then everything you get in between in terms of benchmarking and evaluating model deployment properties and so on. and automating the part that honestly today is kind of done by hand in a lot of what people call the MLOps flows, right? So a lot of there's a lot of folks in model deployment. I'm fully aware of that, and there's a lot of great stuff being done there. So the part that we wanted to, the opportunity that we have with our history and our core technology here is to cover the part that is assumed to be done by a very talented engineer, which is producing the thing that you're going to deploy, and that's the thing that we wanted to automate, right? So um, in the process of doing that, Mihail, since you asked, like, what is TVM's role here? TVMs is an important part, but it's not the only part of the platform, right? So the platform here can use TensorRT and Onyx runtime, and so PyTorch is native stack, TensorFlow native stack, and we support all, pretty much all of the major frameworks for model ingestion and so on. Does that give you a general view of what it is? Yeah.
Yeah, no,
Cool.
absolutely.
Great.
And I think that I'd love to maybe go even one step further here by
Yeah.
by zeroing in on. So, as you said, there's a lot of players in the deployment space, and people have certainly recognized that it's a big problem area for a lot of MLEs and ML teams and data teams. And I'm curious, when you talk about one of the big value adds of something like an OctoML, where you're very deliberate because of your research history with TVM and whatnot, you're very deliberate about this hardware-software abstraction, how you can optimize for different hardware targets, and you're able to be super fine-grained about the level of control you give in, hey, I'm optimizing for this hardware target, I'm these latency concerns, like this throughput, maybe, you're talking about cost per dollar kinds of considerations. I wonder, which are the kinds of groups that derive the most value from that level of specificity in the considerations, right? Because there's also, one could make that argument that there's this whole class of companies that don't even have a single model in production yet. They're just trying to get something out the door. They don't care if it's 50 milliseconds or 25 milliseconds or like 300 milliseconds. They just need something that they can hit inference, they can run inference endpoints with. Where does it sit in that kind of that value chain?
Yeah, no, I love that question. So I would say that we offer hardware independence, like with good performance, right, and automation and really good performance, right. So, and with these three value the props here, depending on the end user, they get value in different ways, right. So for the high maturity users, what they care about is performance and hardware independence, right. So because their models will run faster, so that means they save money running at scale in the cloud, and they give you hardware independence. It gives them more ability to scale, and automation reduces the time that their expensive engineers spend to get those models ready. So that's how they derive value, right? So, but now the product, as you see, probably if you've been following what we've been doing, see that we are going more and more towards broadening the set of users that would that will see value in what we're doing, right? So, and what we're zeroing in here is automation, decreasing the complexity of getting your model ready for deployment. How does it fit in folks that are early in the machine learning journey? Well, so for folks that's still creating the model and figuring out how machine learning is going to solve their problem, we don't cater to those users, right? So we cater to users that once they have model candidates they're going to put into production, we're going to alleviate all of the complexities that typically involves handing off the model from a data scientist or machine learning engineer to a software engineer to go and figure out how to deploy, right? So by shortening that time from weeks or months to hours, I think also closes the loop of it's like they can deploy it quicker, they can collect data and then figure out what is the next iteration of their model early on, right? So anyways, the direct answer to your question is for folks that are early in the journey and less mature, it's really mostly about automation. They probably don't care as much about performance then, unless the model doesn't run fast enough to even be viable, then they're going to care about performance, right? So but I would say that what they care about is just ability to deploy it in a way that it costs less and takes less time. So
these are bigger players then, like these are more mature players in the ecosystem, that maybe companies that have bigger resources that are able to, that have already invested the time and the effort to build out machine learning pipelines, and now are like, hey, we want to run this on this hardware device or mobile, this edge device. That's really where it seems like a lot of the value is being derived.
Yeah, so right now, the high maturity folks will see the value immediately because of performance and hardware independence, and the lower maturity, users of machine learning will see value more in the automation, right? So of just we have if you have a chance to take a look at our CLI demo that we have out there, you can see without writing a line of code, you can get your model in an endpoint deployed and then iterate on it and start in your laptop and then move it to the cloud without changing your code at all. So in that case, you didn't even think about performance. All you care about is that, hey, you've done all this automation of migrating your code from a local version to the cloud version or to different versions in the cloud. And so,
Luis,
I want to add one more thing
you.
to your point there. Oh, sorry,
Oh
go ahead.
yeah.
Yeah, on the high maturity users, one thing that I think important to highlight here is that we spent a lot of effort in making it very easy to integrate with existing DevOps flows, right? So that means living with, you can have a model in a repository, you can call in your CI/CD flow. We have an API that you can send the model, download the container back, and deploy it in a way that does not disrupt existing flows. Because if we did that, it becomes a hard sell for the high maturity users to just go and have to change how they do things just because they might want to use our technology, right? So we like to think that once they do try it and they see the performance and they see the portability, they're going to go and want to change their flows. But we are working hard to make the API be very easy to integrate with.
So do you mainly talk with SREs and people that are doing DevOps, or are you talking more with machine learning engineers?
Yeah, so it's a good question. We talk to both, and again, depends on the level of maturity, right? So the high maturity companies deploying, and the high maturity ML users, right? So tend to have either sometimes dedicated team to ML deployment. So those are the team we talk to. In some others, they have it's just part of the higher end, more machine learning focused SREs. Um, but for the lower maturity ones, I'd say it's more the folks that do machine learning engineering and they have their hands in deployment. So then we talk to those low maturity customers.
So you've got one book behind you, which is Start with Why. I have to ask, why build OctoML? Well, you mentioned
Great.
some things that were interesting to me before about if we have this optimized, if we can make things go faster, it's better for the environment, it's just better for people because they're not sitting around waiting for whatever their hardware to do the hard work. But I'm wondering about your personal journey into creating this product.
Yeah, no, great question. I'm glad you noticed that. I promise it was not on purpose, So we did send this book to everyone in the company, by the way. So I really love that book. Credit to our CMO David Messina, who also loves this book. It's like, no, everyone in this company should read this book. So our vision here is to make AI sustainable and accessible. And I want to break these two words, sustainable and accessible, down just to explain our reasoning. So sustainable, as in faster, more energy efficient, using less natural resources, but also sustainable in terms of human effort, right? So using natural resources is just the right thing to do. And as I said, if you look at, as I mentioned before, if you look at the amount of compute resources going to machine learning, it's the fastest growing category of computing ever. Like, there's a very meaningful fraction of cycles in the cloud and in the edge that is running very tight loops computing linear algebra. We got to make them really, really fast, right, and use less energy because it's only going to grow given where machine learning is going. So make more sustainable from that point of view, and then making more sustainable from a human effort point of view just accelerates innovation, right? So then you want to have human brains with the precious things to focus about the problems that they want to solve and less about how they're actually going to put it in production. And then on the accessible side, remember, making machine learning sustainable and making AI sustainable and accessible to do good, right? So on the accessible side, accessible to as many people as possible. That means that you have just more people creating applications that are compelling and solve problems that are relevant to the world. And then accessible is inaccessible in as many devices as possible because by enabling folks to run AI where it should be run, can enable new applications and more innovation as well. So, and I'm a fundamental believer that AI can create very, very compelling applications that create new industries. But also now on the personal side, I have a passion for biology. I've always had a passion for biology. OctoML, Octo here comes from octopus, amazing organisms that rewrite their RNA. There's a lot of interesting parallels with just-in-time code generation and so on. And I've done a bunch of research in the past on molecular biology and engineering molecular biology for computing purposes. And the reason I'm mentioning this, which seems like it sounds like crazy talk, right? Well, no, the reason I'm mentioning this is that fundamentally, I don't think that without AI and machine learning, you can make sense of or engineer with biology. And I feel that's just the next wave of human evolution is being able to uh, manipulate biomolecules and engineer them and understand them to make life better, to create new types of things that make life better, right? So, and it's so complex that it's beyond our ability to use first principles engineering. So we have to use AI and machine learning. But the levels of performance that you need and the level of I'd say ability to run very, very complex machine learning models depends on making the infrastructure very efficient and sustainable. So now you go deep into how I think about, like, by creating this platform, enabling more people to go and build these very sophisticated models and run them in a viable way. We're gonna enable folks that are gonna engineer biology, understand biology much better. So
Oh, that's so cool to think about. And did you see the Netflix documentary about the octopus?
I see. Yeah, my teacher Octopus. Yeah, absolutely. It's a
Yeah,
great.
so
No,
good.
if you, it's super interesting. You should if you or the audience is interested in that, to look at how Octopus rewrites the fundament the one of the fundamental reasons why they have such complex cognitive processes is because they rewrite their RNA. Like this, literally, normally, the central dogma is it's DNA to RNA to proteins, right? Messenger RNA to proteins. So most of the time, you change the proteins that you express, which dictates a lot of what happens in your metabolism, right? By just regulatory process that block and unblock parts of your DNA. But in octopuses, what they do, they actually generate from DNA to RNA, and they go and rewrite the RNA molecule itself before it gets translated to proteins, which is very, very unique. It's very similar to, a just-in-time compiler that as it's running is generating code that then you're gonna go and run, right? So um, it's a
I love
quick,
that
very
parallel.
geeky aside here. So,
Yeah. So here's the killer question. Do you eat octopus?
oh boy, I used to eat a lot more octopus. Now every time I consider it, I think about how intelligent they are, and it's hard. It's getting harder and harder. Do you?
No, no, yeah,
No,
I'm full
because
vegetarian,
full
which is
vegetarian. Yeah.
why I asked. Not to
I
preach
know.
or
It's
anything, but
no,
I
no,
just see you're
absolutely
geeking out on
understood. Yeah.
that. And then
No,
it's
it's
like, oh, you love it, and then you're like, oh yeah, but let's have some octopus for dinner.
yeah. I know, I know, especially knowing how intelligent, how precious they are.
Yeah.
I must admit it's hard for me to eat octopus today, even though I'm not vegetarian. So
Yeah, yeah, I can imagine. But
uh,
anyway, there is one
we
last comment, and then I know Mihail has got a question. I see him
yeah.
wanted to ask, which is I really appreciate the fact that you're calling out this idea of making things more sustainable with machine learning, because I feel like it always gets overlooked when you have like the new large language model that comes out. The amount of resources that it
Hmm.
took to train that and that it took to actually like create that, nobody talks about the effect on the environment of that.
Yeah, that's right. I'm glad you brought that up because there's a lot to talk about there. We can probably have a whole episode on this, a whole session on that. But I want to comment on a few things. First, I mean, it's important to realize that a lot of the people talk about today is the resources goes to training models, right? So, but for models that you train that are successful, you're gonna do a lot of inference that should amortize the cost of training to a very large. That means that it's okay to pay, uh, you know, a significant amount of computation early on if you can amortize it over a large number of inferences. But inference also has to be cheap, remember, because then it dominates where the cycles go, right? So, and for any popular model that does useful things, guess what? You're gonna do inference trillions of times. So you got to think about that. So people don't think about this in general. The second thing is, I hope I'm not going to sound like an activist here, but I think that it's important to make these huge computational jobs to train models to be as accessible to as many people as possible, and not be behind huge paywalls, right? So here's what I
So
and
true.
I, when you train a language model, so here's a quick thought experiment, right? So if you train a language model for English, right? So and everyone who speaks English will benefit from this. But then, everyone who speaks English also kind of own the English language. So it shouldn't be good if everyone who speaks English could use this model without having to pay for it, right? So this is why I'm glad that people are more and more creating these open and free language models. But that's only the beginning, because now for you to be able to make use of these models, computation has to be cheap enough, right? So, and that's where I think making it very, very efficient is not just about reducing the cost it built in the first place, but also reducing the cost of being able to even use it, right? So, um, and it's great to see all the progress in foundational models where you can train a large model and then use it and specialize for different use cases. And great to see both, commercial and open source approaches to that. So
I actually wanted to go back to something that we talked about previously, which I'm really glad we touched on, which was your
The octopus.
you have these dualities. On the one hand, you're like a hardware, software, compilation, ML guru. On the other hand, you have this very interesting side of research interest in things like biology and molecular biology. And I mean, it seems like there's very different ramifications, right? I mean, when I spent some time looking into what that meant in the context of your research, it was concepts around using DNA as a form of storage and kind of the high information density of fundamentally, biological mechanisms, right? And things like that. So I'm curious, can you talk a little bit more how you bridge that gap from something which is more hardware, software, OctoML, which is clearly more just focused on these types of concerns, and how that eventually will evolve or can tie into what maybe a longer term goal is around using biology in interesting ways for computation and things like that.
Oh yeah, no, you even got the goosebumps here. Thanks for asking that question. So like if I zoom out, the way I see it is just about time scales, right? So if ignoring OctoML and TVM and even the specific use of DNA data storage as research on that, and even I can talk about computing as well a bit. What I'm interested in fundamentally is how do we build better computing machines, that are more energy efficient, that enables you to, really reach the next level of things that you can do with machines to make, human life better, and then create, let's say, the next wave of human evolution, even, right? Because humans design machines that make human lives better, that leads to better. So how do we make computers better? Well, as a computer architect, you have to look at, the history of silicon-based electronics that's about to reach its limits. So you have to think about alternatives, and there's many alternatives forward, including different types of electronics like 3-5 materials, superconducting logic, quantum computing, and molecular-based approaches, right? So, and the way I think about this as a computer architect is that we're gonna have a mix of these things. I don't think electronics is ever gonna go away because it's highly engineerable, but it's reaching its limits fundamentally. So if you're gonna think about the next wave of evolution with computing machines, you have to think about alternative compute methods and alternative data storage methods and so on. And then now, how do I bridge these two things? Well, AI, as I said before, AI machine learning is a fundamental way how you think about computing. That means you have to build good machines for it, right? So, and also you can use that to design the next wave of machines. So that's the bridge here, right? So using computers that exist today, we create tools that enables us to do research and explore new ways to do computation. And DNA data storage is one example, right? So the motivation for DNA data storage early on was we did this really long, I'd say really awesome and long research project between UW and Microsoft. Started about seven years ago or so, asking the question of, okay, so if you could look at the data growth and the ability to store data, there's a growing gap here. And even in the vast assumptions of storage device and ability to store data for all of the mainstream storage devices, the gap would still grow. So you need to find, a more, first of all, viable approach, and second, a sustainable approach to it. We arrived at DNA because, it's fundamentally a few atoms per bit, right? So has been hardened by nature, so it's durable, it's dense, and it's always going to be relevant because it's not going to go obsolete. You're always going to care about reading DNA because it's relevant to life, right? So then when we started looking at this, how do you encode digital data into DNA and writing to molecules and reading it back? There's machine learning everywhere. Like our encoder, how to map bits to nucleotides, is a learn-based approach. When you read DNA back, it's a giant, really, really messy, set of signals that have to go and decode back into bases and that back to bits that use a ton of machine learning. And all of that actually is so big that the ability to run that efficiently was hampering our ability to do research. So like, let's gotta make it faster. So effectively, we use TVM,
No way.
and with a lot
That's
of what we've
awesome.
done, we use to actually make those algorithms faster. But the crazy loop there is that then what we did was, okay, so let's see if we can compute some machine learning kernels directly in chemical form. So there is a paper that we put out last year doing similarity search, like, k nearest neighbors like algorithms in molecular form. And that's how we went full circle. We demonstrated how to do. We actually did in bio. We demonstrated in the lab encoding a bunch of images in DNA and showing how you can actually perform similarity search in directly in DNA form. So
Wow, that
does that
that's
like
crazy.
it might have been a crazy, so, but it's all about timescales, right? So making computers faster today and thinking about how we can make computers faster and better, for the next wave. So
Yeah, because I mean, first of all, that sounds astounding. I would love to read this paper, the one that you just described. The the one question that I have though, I mean, just for all the good properties of the biological kind of substrate that you're using, namely DNA, one question I have is how, the question of programmability, right? Which is something that
mm-hmm,
you described. Even electronics has the big advantage over other
mm-hmm.
sort of mechanisms for doing this. How does that, how does that play into? Because when I imagine something, when I think of something like DNA, I think of like wet lab work, not as easy to
Yeah.
program, more manual labor kind of involved there. How do we bridge that part of the problem?
Machine learning and automation. Yeah, I'm actually being serious here. It's really hard to design any molecular systems just with first principles, the way you design, a mechanical system or even electronics or even a computing system today. So you have to use, which is not first principles, but explore what you need and then do a search process to arrive at a design that does what you need it to do. So that fundamentally is machine learning. And then how you evaluate and validate that in the lab is by using automation, wet lab, robotics to do experiments. This one, because if you just use humans to go to the wet lab, you just don't get the throughput that you need to validate the designs fast enough and turn the design cycle, right? So it's interesting. It's no different than, even think about how building machine learning models today. It's an iterative process that the faster you turn it around, the better and more automation you give, the more you arrive at a design. So there's another parallel there. Creating machine learning models and designing molecular systems today is very much, a process of search, finding a good one, evaluating, learning, and then trying the next one, right? So
I think that's great. I mean,
so that
that's
means that
so
for
it
the
sounds like.
future web, oh, sorry, for the future web, maybe 10, 15 years from now, you guys are talking about the wet lab ops. How do
Ah,
you how do you design better molecular systems and create?
that's that's
And
that's
then
the
you're,
that's going to be the sister
Sorry,
community to the
yes.
MLOps
yeah,
community.
except Luis, you're going to come on and you're going to say, no, that doesn't exist. Don't believe the hype.
You want to come full circle, right? So
Yeah.
We're gonna play that clip. We're gonna actually project
but
the clip. Be like, remember when you said that, and
yeah.
that'll be.
No, that was fun. Yeah. So anyway, wow, this is being awesome. I know we talked about a number of different topics here that all I think comes back to ability to create better machine learning models and deploy them and make good use of them, right? So I want to make sure that we actually touch on some of the key things that you all wanted to touch on, so yeah, so I don't distract you too much here. So
Yeah. Well, one other maybe one question that I had was, because you are a professor also, like in your background. I'm curious. There's been certainly this wave in the last few years of people from academia going into industry, either getting
mm-hmm.
poached by big companies or starting companies. Can you talk a little bit about people for what that transition, being a serial entrepreneur in your case, from academia into industry, and what are the skills that translate, or how's it different, and how to sort of think about that transition?
Yeah, no, well, this it's a pretty big question. So I'll offer some thoughts here, right? First, there's a lot to learn in building a business, right? So I'd say that in academia, you're focused, the output of the work is a fantastic student who's going to go and change the world, and also papers are going to change how people think. And This is very much about how do you create some surprise going to make how people that's going to motivate people to think differently, right? So whereas in industry, what you need to do to build a successful business is build a product that people are going to pay money for and actually make it successful, right? So some of that is similar, which is about okay, so you need to have some differentiation. Sometimes it's a piece of technology. Normally, coming from academia, you have some differentiated technology. Sometimes it's a set of people that think very differently and know how to do things better than anyone else, right? Sometimes it's just a market opportunity that you're a first mover and you have to move as fast as you can, right? So that transition for me from academia to now, I'm essentially I'm full time at OctoML, being full time at OctoML for the past 3 years or so. still spending a little bit of time in academia because it's just part of who I am and less of a job. Um, the things that I realized that I is very very different is for you to be a product organization. It's all about turning any I would say most successful businesses today, even if they started from a technology foundation, eventually they have to become product businesses, because that's what people pay money for, right? So and that iterative process of refining and designing a product and so on, I don't think is similar to how we do research at all, right? So and you have to come to that understanding that, hey, that's how businesses work, and being very diligent about the product and not let the shininess of technology distract you from the fact that you building a product people should pay money for is something that academics really need to think hard about, right? So but now to your earlier point of industry, I don't know if I'll use the word poaching, but I would say, luring academics to
Yeah, I
go to
was gonna
industry. There's
say that.
several motivations for that, right? So some of them just go to do research in industry. It's great to see, companies that have built very successful businesses investing in future research. Like historically, a lot of good stuff happened that way. Look at Bell Labs, DEC Research Labs, and IBM Research, Microsoft Research, and now Google. Like this is natural and it's great, right? So I think that has to be done right? Because um, if you get all of the faculty that are very productive doing research with the students into industry and they stop making students, then wait, so who are you going to hire with PhDs 5-10 years from now, right? So I think industry is now finding its balance and being a lot more flexible in letting people straddle, like be part in academia, part in industry, and keep both going. I think it comes from the realization that if you don't do this, you don't keep producing PhD students, you're not going to have folks to hire in the future at that level of at that level of depth. So that's one point. But now when industry hire faculty, I'd say to do product, often it's because it's in a high tech industry, like something that you're building products around technologies that are pushing the state of the art, and that's what I particularly find exciting. I don't think, definitely not the only way to build companies, obviously, but it's what I think can appeal to a lot of folks that, let's say, especially older faculty like me that have had their impact in writing papers and graduating students. I see building a company out of research that started in academia as a third form of impact, right? So, just there's some thoughts. No answer to your question, but more thoughts, So,
What do you say to the people that feel like academia is out of touch when it comes to the work that they're doing and the impact that they could be having on industry? It's like almost like there's two parallel worlds there. And I've heard some
yeah.
people say, well, it's because academia isn't exactly, or academia doesn't have full range on all of the data that the industry
Yeah.
has. So how can they be making all this impact?
It's a great question. I think ties back a bit to what Mihail asked as well. So the way I tie these two questions, first is that some faculty get really attracted to industry, by the way, because you have access to things for research that you wouldn't have in academia. Often it's a data set. This is true, used to be true in life sciences. Now it's being true in computer science. Like you have access to how the world do search, for example. There's no way to have access to that in academia, right? So now academia being out of touch. I would say that it I I can see where the sentiment comes from, right? Because often academia tries to think about a world that might not be how the world is and solve problems in that imaginary world. Um, in some cases, it actually leads to great ideas that does come back, right? In some cases, it doesn't. What worries me is when academia does research, um, and with the intention of having impact in industry when it's out of touch with industry. So that's the thing that worrisome. I do not mind when you think about, hey, here's let's say a more long horizon research that's not directly motivated by an industry problem, but it's motivated by a fundamental technology trend. That's good. It might be seen as out of touch with industry today, but eventually industry is going to catch up because it's a fundamental technology trend. But now if you do academic research and you try to motivate an industry and that motivation is wrong, that's bad. And there's some research like that. So those are the ones that we should call out, and then hopefully they'll come to grips with that, right? So does that make sense? So
Completely.
and it's interesting to see too. I would say a lot of technology companies being more and more open about opening up data sets, opening up infrastructure for academia to use. This is all ways of actually avoiding scenarios where academia has to speculate too much in what industry is actually doing. And all these efforts, I think, is starting to pay off, right? So
Yeah. Yeah. So quick rapid fire for you before
okay.
we finish this. I want to ask you what the last book you read was.
Wow. So what was it again? Oh, Boys on the Boat.
Oh yeah,
Do
what's that?
do you know do you know about this
No.
book or no? So it's about the I think 1936 Olympics, the rowing club here in the University of Washington that ended up winning the Olympics, being completely the underdog, and then winning. Some of the stories like winning against all odds, but the whole story about it's a bit of history. There's a lot of U.S. history as part of that too. You know, for example, there was a massive sandstorm that happened in the U.S. I had no idea. That was surprising. But the key thing there is just about how for you to win at for a successful crew team to actually make it, you have to have these rowers like be completely in sync with their bodies and how they think, and so like it's all about parallel computing in the end, by the way. So if you don't think this perfect synchrony, lockstep, perfectly synchronized, you don't you don't make it, right? So in every single ounce of efficiency matters there. And I think there's an interesting parallel here with how eventually machine learning models run in computers, that everything needs to be like just perfectly right for it to be efficient. And when I was reading about the level of depth and refinement that this team went to reach maximum peak efficiency in rowing, first of all, it's an incredible story of human achievement, honestly. But also putting like a pure science hat, like, oh my God, hell, this body is at that level of efficiency, every single thing matter, and they synchronize to a perfect degree, made me think of how computers work too. So
That's incredible. I love how you bring the parallels back to computers. And so, what is a company you're in Washington, right?
that's that.
Washington State. What is a company or startup that you've seen that has impressed you lately?
One that has a runway ML.
Yep, we had Brandon on here a few months ago, who was their lead ML engineer. They're killing it. It's so cool what
The
they're
video
doing.
editing with ML,
Yeah.
I think that's one that is really fantastic. So here's another one, A Alpha Bio. So just to bridge computer science and biotech, what you're doing is using a mix of I would say a synthetic biology protocol. The problem that you want to solve is that what is the protein-protein interaction? Like, how do you, because this is important for antibody development, it's important for, diagnostics, drug development, and so on. And they had this machine learning plus synthetic biology approach to use yeast to do a lot of work to produce proteins and then measure how they stick or don't, and read that with DNA sequencing and use a lot of machine learning to produce a data set that informs folks designing vaccines and designing antibodies and so on. That's really impressive what they've done, and bringing together synthetic biologists, machine learning folks, and folks doing wet lab automation and so on.
Wow.
Yeah.
All right, last one for you, Luis. How do you want to be remembered?
Wow. that's wow. That's a good question. I think in bringing the right people together, so building teams, I guess.
Amazing.
Yeah, and it doesn't matter in what context. I feel like it's impossible to do anything big without having a team. Nobody can do big things alone, right? So, and I guess being somewhat remembered. It's not that I have aspirations of having a legacy. It's not like, but I was like, if people think me as somebody who was able to bring the right people together, I'll be very happy. So,
Oh, I like that. I got goosebumps. Well, thank you so much, Luis. This is super cool. Como a gente
thank you,
diz
Yasser.
antes, muito obrigado. Eu estou muito emocionado que você vem para o podcast. E tudo bem para você e OctoML?
Thank you very much, guys. Awesome chat. Hope to meet you two in person, and continue some of these conversations in a pub sometime. So
Yes.
Absolutely. This is fantastic.
We're starting a local meetup in Seattle, so
you are
maybe
cool.
you'll have to drop by and
Absolutely.
hopefully you can
I'll
give
have
a talk.
I'll love to join and bring some other people too and help spread the word here. So
There we go. Awesome.